Okay, so welcome back for the last session of this school. And so just a question before the secretaries go away. Do you need these for lunch now? Or you have it already? Okay, nobody wants it. So me and Augusto, Saverio, you have it, right? Yeah. Okay, so it's fine. Perfect. Thank you very much. And we thank again the secretaries. Please give a round of applause. They're always fantastic. Okay. And of course, also the audio managers for everything. Thank you very much. Extend a thank you to the others also. Okay, so I'm very glad to introduce you Professor Salzo from Università Roma La Sapienza, and they will talk us about, again, statistics. So we began with statistics, we close with statistics, in particular of the least square and lasso estimation, and then in the end, dual computational approaches in machine learning. Thank you, Saverio.
So thank you very much for the kind invitation for the organizers. And it's really a pleasure to be here. So I will talk about two, say, different problems. So in the first part, so the flavor is more statistical. So I will show you how to, methods for assessing the quality of least square estimators and lasso estimators. Okay, I will tell you about where the least square, the classical least square problems, and then the shift towards lasso in these days. They are they target different situations. Okay, so I will show this this change, and then in the second part is more about computational aspects. I will talk about duality in general in convex analysis, and then I will show you how this framework is really fit is at the basis of kernel methods and solving the problem of regularized empirical risk minimization. You saw I think the first day of this school. Okay, so I will start with slides, but then I will soon switch on the Blackboard. So it's just okay. So in the problem of classical linear regression is very old. You have n couple of points. So let me see if I can point. So in general, you have that the x are vector possibly, y are just numbers, and you are assuming that underlying these data, they can be essentially described by linear operations, okay? And the method of least square, so the point is try to estimate this parameter, theta, and the method of least squares essentially consists in determining the parameter theta by solving this problem, okay? So minimizing the sum of the squares of the errors that you make, okay? So this is a, it's very, very old problem. It's, there is a dispute between Legendre and Gauss. So it first was published by Legendre. So the first publication is by Legendre. And in a book that I will now show you. And later there was another publication by Gauss. But in this second publication, Gauss claimed that he knew this method before, when he was 18, actually. And so, there was a dispute among these. Actually, people tend to believe to Gauss because Gauss did much more than Legendre. Legendre was just giving, I will show you, just an algebraic procedure. But Gauss studied also the statistics. Okay, so this is the publication by Legendre. So in this book, in the appendix, so as something that was, just back, there is this this sulle méthode of least squares. So I have the English version because so on least squares. And so you see on the method of least squares here. So I can now a little bit zoom in. So you see that it is about solving linear systems of this form. So X, Y, Z are the unknowns, A, B, C are the known coefficients. And it is, in my opinion, it is instructive, it is to see the motivation. And because he says that if there are the same number of equations as unknowns, there is no difficulty in determining the unknowns, and the error E can be made absolutely zero. But more often, the number of equation is greater than the number of unknowns. And it is impossible to do away with all the errors. And in a situation of this sort, which is the usual things in physical and astronomical problems. So at the Legendre time, the situation was that the number of measurements was much larger than the number of unknowns. Okay, so I will introduce soon what is normally called the design matrix. The design matrix was of this form. Okay, you have many measurements, many equations, but few parameters to estimate. Okay, and that was the setting at that time. And then he says, of all the principles which can be proposed for the purpose, I think there is no more general, more exact, and more easy of application than that of which consists of rendering the sum of the squares of the errors a minimum. Okay, and so you see that is just these are the various equations, number with primes. And it's just computed the derivatives, what is now are called the normal equation. I will show you, and then get the estimate. It's just a few pages, then it's just finished. Okay, so there is no statistics. It's just a way to solve this. Okay. So the important aspect is that nowadays the situation is different. So the situation nowadays is that more often you have many parameters. So the number of parameters that need to be estimated is larger than the number of equations. Okay, and so this is a very common situation. If you, for instance, if you deal with I don't know, genomic data, for instance, you have the dimension of the space is very high. So this is the team nowadays is high dimensional statistics. Okay, so then, and so, but this is just to show you that the least square was thought for this different setting, and therefore in order to handle and to to address this new situation, you need to change this method. Okay, so I will just so the setting that I will explain. So you have the vectors xi, okay, and differently from the setting of the classical setting of supervised learning. So in the setting of supervised learning, you have that both the x and the y's are random. Okay, so in this talk, I will instead and more I will describe the situation in which the xi are not affected by noise, while only the y's are realization of random variables. Okay, this is so the point x are called design points. And this situation, when the design points are not affected by noise, is called fixed design. While the other situation, it is called random design. Okay. And okay, so then you have these vectors. You collect this in a matrix. So you put this in a row, and so you generate a matrix which is n times d. Okay, and this is called the design matrix. So the model is this one. So each one of the random variable yi is of this, suppose we assume that this relation holds for some theta star that we don't know, okay? And we assume that the epsilon, for simplicity, that epsilon I are IID random variables and are essentially normal variable, okay? Normal random variables. You can generalize this model. You can assume sub-Gaussian random variables. You do the same analysis essentially, but just for simplicity, I will treat this case. So, okay, I will use this notation also on the blackboards later. So y equal x star plus epsilon. So in a vectorial form, x is the matrix, and epsilon is a Gaussian vector with this covariance, zero mean and this covariance matrix, okay? Okay, so the least square estimators is computed by solving these problems, right? That in a matrix form can be written in this way. So here, know that x is a matrix, y is a vector, okay? So in order to solve this problem, this is a smooth problem, just compute the gradient. The gradient is this expression here. It's a convex problem, so I can find the solutions just by finding the stationary points, okay? They are the same. So gradient equals 0, and this gives me this equation. This is normally called, they are called the normal equations, okay? So this problem has always a solution because x transpose y is in the range of x transpose, and the range of x transpose x is the same, of x transpose. So this has always solutions. You can see the problem also in another way, because this is about projecting y onto the range of the matrix x, and so it has always solutions. So you can equivalently write the problem in this form. This is the projection onto the range of x, of y, and then you want to solve this equation, okay? This has always solutions. So I'm not assuming any, on the dimensions of x, I'm not assuming any kind of hypothesis, so n less than d or vice versa. So here, in principle, I can have more than one solutions, okay? So among the many solutions, I will pick the one of minimal norm. And this is one criterion, okay, that it is often used. And this leads to the so-called pseudo-inverse of x, okay? So we will set this. So the estimator we are looking at is, so among the many solutions, I will pick the one of minimal norm. Okay, and this is can be essentially written, I will remind you, written in this way. So with this x dagger, which is the pseudo inverse of x, it is called, can be written in this, either this form or this form. And I note that this quantity is a random quantity, okay, because it depends on y, which is a random quantity, okay. So I just remind you about the pseudo inverse of a matrix or operator. So what the way it is constructed normally is that so if I take the matrix X, if I factor out the kernel, right, I get a bijection between the orthogonal of the kernel and the range, okay? And so then I could, so this is the orthogonal of the kernel and this is the range. So if I pick y, I project onto the range, and then there is a bijection between these two, so I can come back and get a theta, okay, in the orthogonal of the kernel. So then this is the way it is defined, the pseudo-inverse, okay? So I project, and then I make the inverse of this, okay? And this gives me, of course, because I am in the orthogonal, the minimal, exactly the minimal norm solution, okay? So, okay, the following property can be proved. So, okay, this is just another expression of the same. For instance, this is useful when you know that this x transpose x is invertible, then this gives you an expression of this pseudo-inverse. This you can put here -1, okay? And the other property is that if you do x dagger, this is the projection onto the orthogonal projection onto the range of X, okay? And this is clear from the way it is constructed. So I will use this property in a moment, okay? So again, this is the estimator, okay? So what we, okay, I need just to remind you, we will, deal with the random vectors. So just a reminder, when you have a random vector, the expectation is just the expectation of the components. Okay, it's the vector composed by the expectation of the components. And the covariance matrix is the matrix of the covariances among all the components of the vectors, okay? So it can be written in this form. This is the transpose, so it's the external product, okay, between these two vectors. And the entries are this one, okay? There are simple, it's, of course, the expectation is linear, it remains linear. So when you multiply by a matrix A, and the covariance works in this way, the covariance of a matrix A times a vector transform in this way, okay, is A covariance and A transpose, okay? So this is just to prepare for the analysis, the statistical analysis of a linear of this estimator. Okay, so what we want to actually estimate, okay, is not really the parameter. As I told you, it might be that you have more than one solution. Okay, we pick a criterion, which is that of minimal norm, but we really don't care about the parameter. What we really care are the value of the, say, our model, our functions on the points, okay, on the given points. And we want then to, what we want to really estimate is this quantity, or this vector here, okay, which is x theta star, not really theta star, okay? And we estimated these vectors by this estimator, okay? So then it's about, so this is the quantity, the estimator, and this is the quantity we want to estimate. So it is easy to see that, so let's see. Okay, so this estimator here is unbiased. So if you make the expectation, okay, it's linear, so we saw already. So you replace this by the definition, which is x dagger y. Then this goes out of the expectation, and then you have x dagger, and then x star theta star, which is the expectation. If you recall the model, the expectation of y is x theta star, and now x theta star is in the range of x. This is the projection onto the range, so it's the identity then, okay? So it's just, it does nothing, okay, because it's already in the range. And so you see that this, the expectation of this is mu star, okay? So it's an unbiased estimator. And then you compute the covariance metric of this, which is sigma square and then xx dagger, okay? The covariance of this is, again, the definition of this is xx dagger y. So we are in a situation in which this is the A that I showed before. So it works in this way, but now, since this is a projection or orthogonal projection, it is also symmetric. So the transpose is the same. And so you have this equality here. And now the covariance of y is sigma square identity. And now you remember that this is a projector, and therefore the square of this projector is the projector itself. And so you have this, okay? So by the way, I mean, if you have any, you can interrupt me when you wish, in the sense that if you, it's, we are few, so we can interact freely. Okay, so these are the two quantities now. And now, in order to assess the quality of this estimator, the quantity you should look at is this mean square error. which is defined in this way, okay? 1 over is the average squared error you make, okay? And this can be written in this way, right? And is the same as this quantity here, okay? So the theorem, simple, that I will show just a few lines, is that if I call R the rank of X, so this is still a random quantity, okay, because it depends on this, which is random. The expectation of this is sigma square R over N, okay? The important aspect, so this is an equality, so it really tells, so you can also find as an inequality the same sort of bound also in high probability. So you can prove that this mean square error is less or equal than this guy, and at the numerator then you have plus logarithm of 1 over delta, where delta is the confidence okay, level. So with probability greater than 1 minus delta, you can prove that this MSE is less or equal than this with the numerator is a logarithm of 1 over delta, okay? So, but the point here is this R, okay? So the point is that if X, for instance, is full rank, so R is the minimum between D and N, and so then you have this situation, okay? And so this is the dimension of the space, and this is the number of measurements, okay? So the problem with this bound is that if D is larger than N, this is 1. And so you cannot make this error going to 0. Okay, so this is the problem. So you see then, you know, with this statistical analysis, what is the problem of least square? Okay, it really is tailored for, you know, the situation in which N is larger than D. Okay. So the proof is really a few lines. So it's just, okay, I remind you, yes, this is the definition of the covariance of a vector. So the point to note is that we are looking essentially at this quantity because our estimator is unbiased. So here we have we will have here, right? So this is the mean of this quantity. So it's this one. And so since the entries of the covariance matrix are this one, so this quantity here is nothing that the sum is the diagonal, right? Is just the sum of, is the trace of this covariance matrix. Okay. And therefore, so the expectation of this is 1 over n of this, and then 1 over n the trace of the covariance matrix. The covariance matrix is of the form sigma square XX dagger. So it's linear, sigma square goes out. And the trace here, this is a projection, orthogonal projection. And so it's just, you know, all the eigenvalues are 1, and the dimension is, and the number of those are of non-zero, right? Non-zero are exactly the dimension of the space of the range of X, okay, which is R. So it's super easy, okay? So this is that's finish. You know, this is the conclusion of the analysis of least squares. Okay, so now we'll see the rest for the lasso on the blackboard. Okay. Okay. So what I will now I will talk about the statistics of lasso instead. Okay. You will see lasso is a variation of this least square, of the method of least squares. And it's about the situation, you know, it deals with the situation of the dimension of the space, which is larger than the number of equations. So, so what we are assuming now is that we have always the same model, essentially, okay, which is yi, so then xi theta star plus epsilon I. epsilon I is the usual is n0 sigma square. And what we now assume, so now we are, you know, the dimensions here are, we have n equations, okay, so the usual x is in R n times d. And the situation we will, you know, look at is the situation in which n is greater than n, okay? So we have to imagine that then the data are in this high dimensional space. And the point is that what we essentially assume is that this vector here is sparse, okay? The vector we are looking at is sparse, okay? There is a way to, you know, is that normally it is denoted with norm 0, so is the cardinality of the support of theta star. Okay, support, I mean the indexes where the components are non-zero. Okay, and so I assume that this, you know, is possibly much smaller than the dimension d. Okay, I think that perhaps Professor De Vito will show a situation, right? So you have normally, you have, if you, for instance, you are dealing with images, often, you know, you may think that the true dimensions of the data is much smaller, okay? And so, okay, and the lasso estimator is defined in this way, then, as theta hat L1, which is the argmin over theta, which is in RD, of 1 over, so is 2n, then x theta minus y square plus lambda theta 1. Okay, so this will be the definition of our estimator. Okay, you see there is a regularization parameter, lambda greater than 0. So it's a kind of, so there is a penalizer, essentially, so which is this one. This is the L1 norm. I guess you know already, right? It's just the sum of the absolute value of the components. So I will provide you some, say, just general consideration about why this should give you a sparser vector, okay? And then we will analyze instead the statistics of this, okay? So if you write down, I think you saw the, you know, if you apply Fermat rule here, you write down the optimality conditions. So you will write down this, 0 belongs to, so it's 1 over n, and then x transpose x theta minus y, and then you have plus lambda and the subdifferential of the norm 1 theta. Okay, so then if you sum theta to both sides, you bring this from this side, and then you sum theta, then you will have that theta minus 1 over n x transpose x theta minus y. This belongs to theta minus plus lambda subdifferential of norm 1 theta, and this is nothing that identity plus lambda subdifferential of norm 1 theta. So I think you saw, you can invert this and you have the prox. Okay, so then you have that theta is equal, you have this fixed point equation, prox of lambda, and then norm 1 of theta minus 1 over n, and then x transpose x theta minus y. Okay, you have this fixed point equation. Actually, this prox of the norm 1 is what is the soft thresholding operation. So this is the same as a theta equal soft, I will explain in a moment, theta minus 1 over n x transpose x theta minus y. This soft thresholding acts component-wise, and the way it acts is this way. You have lambda minus lambda, and then you have this operation here. So what happens is that when the entries here are less than in absolute value than lambda, they are actually killed. Okay, they are actually put to 0. Otherwise, they are slightly shrinked. Okay, so the point is that then this is a fixed point equation. So this probably will have, you know, some of the components will be killed. Okay, that's just you know, kind of qualitative consideration. Okay, so there are also other reasons which look at the unit ball of L1, because this problem is essentially equivalent to that of solving this problem, minimizing this quantity on the L1 ball. And so if you think of here of the, you know, the level sets, it might be that you often minimize, you know, the minimum over an L1 ball, it often will happen to be in the edges, okay, in the vertices, okay, of the L1 balls. And on the vertices, of course, you have fewer components, right? Okay, so what we will now instead look is at the statistics, okay, of this. Okay, so okay, so I will do this way. I will proceed. Okay, so we, by definition, right, I can say that this x theta minus y square, so that hat L1 plus 2n lambda theta at L1. So this is the objective function computed at the minimum, okay? So this will be less or equal than x theta star minus y square plus 2n lambda theta star 1, okay? So I just apply the definition, okay? Again, stop me if you if something is not clear. So then from this, okay, I will also see, yeah. Or maybe you, okay.
Sorry,
yes.
I cannot understand this inequality because I would have said I mean the theta star is the optimal one, right?
The theta star is not the optimal.
Ah, okay.
Theta
okay,
star
okay.
is the parameter you are looking at. Okay, you know that. So the theta star is the one that verifies this x theta star plus epsilon. This is a statistical model. Okay, you have, this is the random matrix. You are assuming this, okay, that there exists a theta star that satisfies this equation with epsilon, which is a Gaussian random vector. Okay. That's it. That's theta star. Now the point is how to estimate this theta star, say, or the value, or even this quantity. Okay, it's kind of denoising problem. Okay, because I want to estimate this, but there is noise. I just have access to the y's. Okay. So then what I do is that I have to construct my estimator by relying only on what I know, which is y and x. Okay. And so that's the definition of there. You see there is a y, there are x, the design metrics. You estimate theta L1, hat L1.
Yeah.
And now you want to judge whether this estimator is good or not, right?
Okay.
With respect to this theta star, which is, is something that you don't have access to, but
exactly.
theoretically it exists. And just so this is right.
But okay, so then why is this inequality in this way? Like
the inequality is because by definition, so I'm looking, so theta star exists. I define theta hat L1 in this way.
Yeah.
It is the theta that minimizes this quantity, so that achieves the minimum, okay? So then if I plug here the theta at L1, the objective function will be less than to the same objective, but computed at theta star.
Okay.
Okay?
Okay, so they
No,
both relies on the same data set somehow.
Sorry, say again?
Sorry, the n is fixed in both sides, right? So
what is fixed? Sorry.
And the number of rows in my
absolutely.
So
we are playing with n fixed.
Okay.
Now, of course, in the end, we will have a bound that incorporate this n. So then you will see a different situation with what we saw for least squares.
I see that. Okay, so the logic is that the only thing that I know is the fact that I'm minimizing this quantity. Then
yes.
Because of the fact that I'm not saying nothing about theta star, then I can write this.
Yes.
Okay. Makes sense.
Okay. Okay. So this we have this inequality, and then we can. You will see is just about, we have to, it's algebra plus random algebra, kind of. So then we have that x theta L1 minus y. I can write this same quantity in this way. So is x theta at L1 minus x theta star square plus x theta star minus y square. And then plus 2 times x theta star theta hat L1 minus x theta star, and then x theta star minus y. Okay, I just developed the square sum and subtract x theta star. Okay, so okay, this guy here is nothing but minus epsilon. So the quantity, essentially, I will always assess the quality of this estimator by looking again at the mean square errors, okay? So the quantity that I care of is this one, okay? So this quantity here, then, is equal to this minus this quantity, okay? Minus this and minus this, okay? But this quantity is is present also here, and this guy is less or equal than that quantity minus this, okay? So what I can say then is that, okay, is that x theta hat L1 minus x theta star square, this will be less or equal than okay, so is here is this, so I will have x theta star minus y square plus 2n lambda, then there is theta star 1 minus theta hat L1, 1, and then minus this guy, x theta star minus y square, and minus this, which means plus 2 x theta at L1 minus x theta star epsilon. This goes away with this. So in the end, I have that x theta at L1 minus x theta star square, this is less or equal then 2n lambda, then theta star 1 minus theta at L1 1 and plus, so this x, I will bring x from this side, this will be x transpose epsilon, then I will apply the Holder inequality. So I will majorize this with, this will be less or equal, so this will be 2 times, and then the norm of the theta at L1 minus theta star 1, 1, and then x transpose epsilon infinity, norm infinity. Okay? So is this, I majorize this, okay, I bring this x here, then this becomes theta L1 minus theta star, and then x transpose epsilon, and then I will majorize this by the Holder inequality, so I will take the norm 1 of this and the norm infinity of this, okay? So then I have this relation.
Sorry,
okay, so
Mario,
yeah.
just a question. So the parenthesis closes after.
Sorry.
Norm 1. Okay.
So this is something that. Okay, so I don't know if I have time to do it. We'll see. There are two kind of bounds that you can get for this lasso estimator. The one is called slow rates, and the other fast rates. So you will see is about, there is a square root that disappear in the fast rates. Otherwise, you have a square root that will be a slower rate. And the slower rate holds without any additional hypothesis on x. Okay, you don't need to make assumption on x, essentially. Okay. Otherwise, in order to have faster rates, then you have to make assumption on x, which are common also in compress sensing, in other, okay, they are called incoherent matrices. So the analysis is, the two analyses actually go in parallels till here. Okay, so then, and from here they diverge, okay? So now I will present the slower rates, and if there is time, so then actually I have also some written notes in case you are interested. I can give you. So this is we will start with this.
Sorry, may I ask a stupid question?
Yeah.
So the stupid question is, so in other lectures,
yes,
we saw sometimes that you do this trick with the squares so that you get the error there, but then you take the hope and it disappears because the average of epsilon is 0. So here you can't do it because theta hat depends on the noise, or why can't you do it?
Yeah. So the point is here, this is something that depends, is a random quantity, right? So if the point is that you will see, so the point is that I have to get rid of this actually now in the bounds. This is a problem, okay? And you will see now the how this will, it is achieved. But you suggested instead of what, so of keeping, what was it? So I didn't get completely the point.
Taking the hope.
Okay.
Right, so averaging out.
Okay.
So because what you want is actually what you say that
but
is
now,
you want the hope. So doing the hope there, because I think in the other cases
the average, the hope.
Yeah, the average,
okay,
the expectation. Sorry,
the hope is something that.
yeah, sorry.
The expectation.
The expectation.
The expectation that here you have two random quantities, right? So you cannot.
Yeah, which are correlated, because in the other cases they were independent of each other, but in this case, because there is maybe the point is that the other estimators, when you have L2, you can write it down, and so you can write the precise dependence on epsilon.
Because,
and so
one important point is that this estimator is nonlinear. So when you deal with linear, you saw the least square was a linear estimator. It was expressed, the relation that linked the estimator to y was linear. Okay, now it's not linear anymore, and then the things are more complicated. Okay, so from this inequality, I will have that x theta hat L1 minus x theta star. So I will now majorize this by the triangle inequality, and then I will get that this is less or equal than, so let me see, is 2, then x transpose epsilon, infinity. Then there is a plus n lambda, and then there is theta star 1, and plus 2 x transpose epsilon infinity minus n lambda, and then theta et L1, 1. Okay, if you apply here the triangle inequality, you will have these same terms, okay, but with plus. And then you see here there is n lambda, and here there is this norm infinity. So then you can arrange the things in this way, okay? So now we are almost done. So the point here is that, as I said before, what I don't like is actually this term. And the reason why I don't like it is that here there is a random quantity. Instead, here there is a quantity which is not random, okay? And I made also a hypothesis somehow on this, okay? Somehow I am making the hypothesis on this that is sparse in some sense, okay? So I want to remove this, and the way I do, since this is minus, I will make this quantity, which is a random vector, less or equal than n minus lambda, in order to get rid of this, okay? This will be negative, okay? So now the point is that I will get a bound in high probability of this. So I will look at this less or equal than n lambda with high probability. Okay, that's the purpose. Because in this case, then I will get with the same probability, this will be 0, and then I will get that this will be less or equal than 2, and here there is a n lambda and n lambda, so I will have 4 n lambda, okay, with a high probability. So, and this in the end will give me the bound. So then I need to analyze this, okay? So x transpose epsilon. Okay, so we put the data in the matrix X as row vectors, okay? So if I look at X as xij, so 1 less or equal than I, this is n, and 1 less or equal than j less or equal than d, okay? This is n by d matrix. So here, okay, I should look at, so here there is, so the components of this vector here are actually, okay, so let me see. Yes, are actually the products, so is the scalar product between the columns of X and epsilon, okay? So I will denote the columns here as X dot J, okay? And this is a vector in Rn. And this X transpose epsilon is nothing but the vector with the X dot 1 epsilon, and then X dot D epsilon. Okay? These are the components of this, okay? So then I'm taking the norm infinity of this, okay? So the norm infinity of x epsilon is just the maximum over j of the absolute value of the entries, right? So x dot j epsilon, okay? So now you can see that. So the point is this is easy. This is still a Gaussian random variable, okay? So then, and this is the maximum. What I will do now is what is normally called union bound. So I will estimate so I will estimate the event x greater than n lambda. This is a maximum. So this will be the union 1D of the events x dot j epsilon greater than n lambda. Okay? So if this is greater than n, there must be at least one which is greater than n lambda, right? So if this is greater than n lambda, there must, so this is the union. And so that means that the probability of this event greater than n lambda, this will be less or equal than the sum of d of the probabilities of this event. So x dot j epsilon greater than n lambda. Okay? And now I need to estimate this. But this is a Gaussian. Okay, I can show you that. So this x dot j epsilon, what is it? This is the sum with I from 1 to n of xij epsilon I. Okay, this is a Gaussian. The mean of this is the mean of this. These are zero mean, so the mean is 0. And the variance, they are independent. So the variance of this guy, x dot j, they are independent, is the sum of the variances. There is xij, this becomes square, so this becomes the sum xij square, and then the variance of epsilon I, which is sigma square. So in the end, you have the norm of x dot the square of the Euclidean norm of the columns times sigma square. Okay, so it's a Gaussian. So then this guy is a normal vector, zero mean, and variance, which is this x dot j square sigma square. Okay, and okay, now in general, right? So you have this situation for if zeta, if zeta is a Gaussian, is a normal variable with the, say, okay, sigma square, say, you have that the probability that the absolute value of zeta greater than t, this will be less or equal than 2 times the exponential of minus t over 2 sigma square. Okay, you have for normal random variables this bound on the tails of the distribution. Okay, so this guy is less or equal to this exponential here. Okay, so therefore we are in this similar situation. We want to estimate this, right? So this will be, less or equal than the sum j from 1 to d of the, so 2 times, and then the exponential of minus. So here, instead of t, I have n lambda. So I will have n square lambda square over 2 times the variance. The variance is this one. So then I will have the norm x dot j square and then sigma square. Okay? So now I need an hypothesis.
So just a question.
Yes.
So there on the general is t squared. No?
T square,
Because
sorry.
you used it with this.
Absolutely,
Okay.
sorry. Yes, thanks.
Makes more sense.
Yeah.
Thank you.
Yeah, thanks. So, so now we are almost done. Okay, I don't need this. So now I need an hypothesis. So the hypothesis is that I assume that the norm of the columns grows, so are less or equal than, say, m and then square root of n. Okay, so this is a vector in Rn. Okay, so what I'm assuming is that, you know, if, for instance, if you assume that the components of this vector are, you know, uniformly bounded, okay, you are in a box, okay, the components are bounded, then you can majorize this in this way, okay? You take the square of the Euclidean norm, and, you know, if each component is bounded by m square, by m, then you will, you know, majorize with the, right, so if you have this, this will be the sum of x ij, and this will be m square, and then n. Okay, this is the dimension. And so you will have this kind of bound. Okay, so then I make this hypothesis, which is reasonable. I'm just assuming that I'm essentially I'm not making a hypothesis. You know, so even in high dimension, this is not a problem. Okay, in the sense that I'm in a box, and that's so with this hypothesis, what I can so with this hypothesis, if I look here, I can majorize this norm with m square n. Okay, so in the end, I will have that. So let me see. The probability that x transpose epsilon is greater than n lambda, this will be less or equal. So here I will put m square n. Okay, I can majorize, of course. And so they will become all the same. So this will be 2 times d exponential of minus n lambda square over 2m square sigma square. Okay? So that's the bound. Now I have just to invert this. So I will put this equal to delta. And so this will gives me, so 2d, so exponential of this quantity equal delta, this will be that n lambda square over 2m square sigma square. This is the logarithm of 2d over delta. Okay, so this is n lambda square, and here there is 2m square sigma square. Okay, I'm just inverting this relation. And so this will gives me that lambda is equal, so to m sigma square root of 2 logarithm of 2d over delta over n. Okay, that's the choice for lambda, for the regularization parameter. And once you do this, then what I have is that, so we found that the probability of this event is less or equal, then I can say that with that choice, the probability that this X transpose epsilon infinity greater than n lambda, this will be less or equal than delta with, okay, and hence, if you wish, the probability that X T epsilon, this is less or equal than n lambda, this will be 1 minus the probability of this, and this will be greater or equal than 1 minus delta. Okay? So in the end, I reached the end. So I found that if I pick lambda in that way, so if I pick lambda in that way, I have that this X transpose epsilon infinity is less or equal than n lambda with probability greater than 1 minus delta. Delta is arbitrary, but lambda must be taken in that way. Okay? So if I now come back to the bound that I saw at the beginning, so that I wrote at the beginning, this should be so x theta hat L1 minus x theta star square. This was less or equal than 2 times, let's see if I remember. So there was a theta star, and then there was X transpose epsilon infinity plus n lambda. And then there was the other quantity, right, in which there was this minus, okay? But now I'm assuming, I know that that X transpose epsilon, this is less or equal than n lambda. Sorry, I wrote this here. So this is less or equal than n lambda. And therefore, that term can be discarded, okay? So then and now this is less or equal also than n lambda. So in the end, this is less or equal than 2 times theta star 1. And here, okay, there is 4 and then n lambda. This is the final bound, okay? There is 2, n lambda plus this 2, there is 4 times n lambda. And then there is this. And the lambda is we know the lambda, so this is 4 m sigma theta star 1, and then square root of 2 logarithm of 2d over delta. So what I know is that now this is, sorry, this is less or equal than this, okay, with probability larger, greater than 1 minus delta, okay? With probability greater or equal than 1 minus delta. So, and this is the bound, okay? This is the final bound. Sorry, I will write better. Okay, here there must be an n, indeed, that I miss. This is 4n. So I should divide by n. So in the end, if I divide it by n, I will have MSE of this quantity, x theta hat L1, will be less or equal than what I wrote. So 4 times m sigma theta star 1, and then square root of 2 logarithm of 2d over delta over n, okay? So that's the final bound. So with probability greater than 1 minus delta, okay? So now you see the difference. because here the dimension occur within a logarithm, okay? So then here, essentially, you can make this quantity small then, okay? So and of course, the important thing is that also, you know, this plays a role. This is the norm one of it. So if this guy, this is a vector with d components, okay? If the point is that if this norm is not grows, with the dimension d, in a proper way, okay, not too fast, then anyhow you can make this smaller. Okay, for instance, let's assume again that the entries are bounded by some constant b. Okay, so the norm infinity of theta star is less or equal than b. And if I call with, again, theta star, the norm 0 of theta star, the cardinality of the support, right? So this norm 1, theta star 1, will be less or equal than b, and then theta star 0. Okay, so I can make, instead of here, I could put b times the cardinality of the support of theta star. So if the if the non-zero components then grows not, not fast, not very fast, then I can anyhow, for instance, if you assume that this theta star 0 is of the order of, say, d to the alpha, I don't know, logarithm gamma d, with alpha, which is strictly, so is less than 1/2, then this will go to 0 as d tend to plus infinity. As long as n here, you can, for instance, take a fraction of d, you can make n equal, I don't know, q times d, with q which is less than 1. So that's a situation in which n is less than d. Okay, so then you will have d in the bounds, only d, and you will see that, you know, this will goes to 0 as d tend to plus infinity. So the point is that these bounds now, because of the dependence of the dimension here, the dimension occur within a logarithm, this can be made small. Okay. So this is what is called the slow rate. And the reason for this is this square root. Okay. The fast rate remove this square root. So then this will go to 0 faster. Okay. And in order to do this, you have to make additional hypotheses on the matrix X. Essentially, what you are making, what you should do is to you know, the only hypothesis I make is this about the growth of these columns. Actually, here you need kind of much stronger assumption, which is called, in the literature, is called the incoherence of the matrix. You assume that X transpose X over N minus identity, this norm infinity, I means, so the maximum of the absolute value of the entries of the matrix, this is less or equal, okay, there is a constant that they put 32, k with k, which is in a n star, so it's an integer. So essentially, if this is small, okay, if you consider this situation equal, so this tells you that the columns, the norm of the columns are exactly square root of n, and they are, and the columns are orthogonal, okay, to each other. Here you relax a little bit. So if you make this hypothesis, actually you cannot handle, of course, the case. This is suitable, this hypothesis here, only for the case that n is greater than d. Okay. Yes. Yeah. So what's the time now? Okay. So
I am a little bit. I still
shocked.
no, I'm not shocked. It's
Sorry.
very interesting, but and everything makes sense. But I'm a little bit stuck with the convergence to zero of this quantity.
Yeah. Okay.
I mean,
yeah.
At
No
a
worries.
glance, I would have said that actually this thing here goes like d square log gamma of d.
Okay, so you can do this, right? So I can explain in a moment. So we are looking at the situation. For instance, one situation is that we are looking at the situation in which n is less than d, right? And then sorry, because you see here I wrote that this is of the order d to the alpha, with alpha which is less than 1 alpha. Okay, of course, because the square root of okay.
Sorry. Okay.
No worry.
I thought it was d square and nothing makes sense to me. Okay.
Yeah, the point, the point is that again, the underlying assumption is that your model, so the theta star you're looking at, is a sparse vector, does not grow, the support does not grow much, okay? And so if this is satisfied, then this makes sense. Okay, so then I was just commenting on the fact that if you assume this other hypothesis, that is called incoherence, okay? Incoherence, then you have the same bound, and if you are interested, I can give you, is, so the starting point of the analysis is the inequality that but then you don't apply the triangle inequality, so you have to do a little bit, and there is also, yeah, is only this actually. So this is a stronger hypothesis, okay? And if you, I don't know if you are, there are a number of these kind of hypotheses that are also common in compressed sensing. This is a really related topic to compressed sensing. And the other point is that, okay, once you ask this, the second question is there any metrics that satisfy this? And the answer is yes. If you take random metrics, for instance, with the entries that are Rademacher random variables, that means they assume 1 minus 1 with equal probabilities, then you can show that for n large enough, this is satisfied again. So the probability that this holds is greater than 0. So there must be at least. This is kind of the type of results that normally they give.
So just a question. So
yeah,
that matrix is n by n, or is it d
this
by
is d by d.
Okay.
This is d by d.
Okay. It's
and it is ID.
And so
you are comparing columns,
column,
right? Yeah.
So, okay,
You are comparing columns.
Should be orthogonal to each
kind
other.
of yeah. The kind of assumption that normally they make is about this orthogonality, almost orthogonality of this event, of the columns. Okay, so the time is, I can, okay. If there are any questions, I'm happy to answer.
Okay, so finished. I asked. So thanks to Professor Salso for these wonderful lectures. So again, if you have questions, comments now.
Or in front of a coffee is the same.
Yeah, exactly. Otherwise, we can do the coffee break and then we resume. And meanwhile, we can ask questions. Okay. Thank you again.
Thank you for listening.
Okay, so we can resume the last lecture of Saverio and the last lecture of the school.
Can you hear me? Yes. Okay. So, okay, so in this second part, so the program is to now to look at duality in the context of machine learning. And so the purpose is, so in machine learning, there is, so I think you saw this, the method, you know, this paradigm, if you wish, which is that of minimizing, so the regularized empirical risk minimization. So you want to minimize the risk, you compute the empirical risk, you regularized, and then this is, you know, a way to get an estimator of your function, of the regression function. This is done normally in reproducing kernel Hilbert spaces. And this leads to a problem, which is in principle is infinite dimensional, right? And so there is then the question how to solve this problem. And there is a standard way to approach this problem, which is via duality, okay? And this is the basis of the so-called kernel methods, okay? And you will see how, so handling, you know, how analyzing this problem, the kernel will pops up somehow, okay? It will pop up in a natural way. Okay, so in order to do this, I needed to talk a little bit about general duality. So the duality I'm referring to is the so-called Fenchel-Rockefeller duality. It's I will explain. And okay, so I think you already saw the Fenchel conjugate. Okay, so if you have a function f from x, now this x is a Hilbert space. So xf from minus infinity plus infinity, this function is proper, convex, and lower semi-continuous. So we denote the set of those functions gamma 0x. Okay, I don't know if you already saw this. So you take a function, you define the Fenchel conjugate, which is denoted f star, is still from x to minus infinity plus infinity included. Defined in this way, so f star of u is the sup over x of xu minus f of x, okay? So this is called the Fenchel conjugate, okay? Fenchel conjugate. Of f. So the properties of this Fenchel, of this transformation is that this is a theorem of Fenchel-Moreau. Is that f star is still in gamma 0x, so it is still proper convex along with semi-continuous, and the dual of the dual, so the star star is f. So if you apply twice this transformation, you go back to f, okay? It's an involution of the gamma 0 operation, okay? So now, yeah. Yeah.
Sorry, does it work for any X space, or it should be reflexive? Like,
okay, so at the moment I talk about Hilbert spaces.
Okay.
Okay,
yes,
that's the setting, okay, for that we need. Actually, you can do this in Banach spaces. I think you need the reflexivity. So let me see. I'm not sure. No, the point is that you can put actually two spaces in duality. Okay, you have to deal with so you have to endow, you know, the spaces with the weak topologies. As long as you endow the spaces, so if you have a pairing between two spaces, so the answer is yes, as long as you consider the right topologies. Okay.
Mm-hmm. Okay. Thank you.
But you know, in this context is we deal with Hilbert spaces. Okay. So Okay, so now we need few facts. I will use a few facts about this Fenchel transform. So the first one is that so f of x plus f star of u is greater or equal than xu. This is the Young inequality. The second fact is that f of x plus f star of u is equal to xu if and only if u is in the subdifferential of f at x. And the third fact is that u belongs to the subdifferential of f at x if and only if x belongs to the subdifferential of f star at u. Okay? So this last one says that essentially the subdifferential of f and the subdifferential of f star are inverse of each other. Okay? Here, this is the Young-Fenchel inequality, the Young inequality, and you have, in this inequality, you have equality if and only if u belongs to the subdifferential of f. So it's a way to characterize this situation, okay? So the framework of Fenchel-Rockefeller duality is this. So you have this problem. So you have a function f in gamma 0 x, and then you have a function g, which is in gamma 0 y, two Hilbert spaces, and then you have a bounded linear operator, xy, bounded linear, okay? And then you want to solve this problem, is the minimization over x, which is in x, of f of x plus g of ax. Okay, this is what we refer to the primal problem. Okay, f of x plus g of ax. So consider that we are dealing with extended real valued function. So extended real valued function. So plus infinity is allowed. It's a way to incorporate constraints. Okay, automatically. So this is the primal problem. The dual problem, in the sense of Fenchel-Rockefeller, is this one: the mean of u in y, and then you have g star of u plus f star of minus a star of u. Okay? So this is the primal problem, and this is its dual. Okay? It's also a minimization problem. I will comment on this in a moment. One thing that you should notice is that it is exactly of the same form of the primal. Okay? The structure is the same. I have a function and then another function, convex function, composed with a linear operator. And another things that you should notice is that if I make the dual of this, I will have this. Okay, so the dual of the dual is the primal. Okay, this A star now, sorry, this A star is the transpose. Okay, I use so in this context often they use a star because the dual operations are often denoted with star, so it's just a consistency notation with this G star, it's everything, every dual operation is denoted by star, okay, but it's the transpose. So the way to, I will show you just the way to derive, so you can derive this, just in order to, if you look, so you can formally derive this via Lagrange duality, okay? And the way to do this is this. So you write the primal problem in this way is the minimization over x and y with the constraint that ax is equal y of f of x plus gy. Okay? So I can impose this constraint, and then I, introduce another variable, which is y, okay? So now, formally, I can define the Lagrangian, which is x, y, u, and this is f of x plus g of y, and then the constraint is ax minus y, and then the multiplier is u, okay? This is the Lagrangian of this problem. And one thing that you should notice is that if I take, say, the sup over U of this LXY, what I get is that, so you look at this. So if AX is equal Y, the sup is over U, okay? So if A of X is equal Y, this is 0, and therefore the sup is constant, okay? So this sup is actually F of X plus G of Y, if AX is equal Y. Otherwise, if F of X is different from Y, right? I'm taking the sup over Y, this is different from 0, this will reach plus infinity, okay? So then it is plus infinity if A of X is different from Y. So then this quantity is the objective function, but it also takes into account, you know, the constraints, okay? So then I can write the so I can write the primal problem in this way as the minimization over X and Y of, say, the sup over U of this LXY U. Okay, so let's assume that, you know, the primal problem, since we care about the values, I will write this as an inf. Okay, so I have this problem, which is an inf sup. I swap inf a sup. This is the theory of Lagrange. So it's sup over U of inf over the cap, so xy of this LXY. So I'm assuming that this equality holds. I can do this. I will comment later on this. So this will be then the sup over U on the inf X and Y of what? Of F of X. So the Lagrangian is here, is there. So I will divide this scalar product here, and I will write that in this way. So it's F of X, so it's minus, okay, I will write this in this way, X, and then minus A star of U. Okay, I bring A to the other side, so it's A star of U, and then I put two minus signs, okay, so it's the same. And then there is plus G of Y, and then it remains minus Y U. Okay, so then now you have this term here and this term here. The X and Y are, you know, separated. I can take the inf separately, and then you can recognize that this is nothing but sup of U, and here there is a minus F star of minus A star of U, and then minus G star of U. Okay, and so if I will call this phi of X, the primal objective, and this is psi of U, the dual objective. So this is nothing but the sup of minus psi of U. Okay, so in the setting of Lagrangian duality, the dual problem is always often, say, always presented as a sup, as a maximum. And so you see that essentially the dual problem is that of maximizing minus psi, which of course is equivalent to minimizing psi. Okay. So instead of, so equivalently, this dual problem D prime can be formulated as a maximization problem, okay, where I wrote minus psi of U. Okay, it's the same. So what is the relations between primal and dual problems? I can show you in a moment. So you have this result. which is that phi of x is greater or equal than minus psi of u for any x and y, and u, sorry. Sorry. Yes. So this is equivalent to show that phi of x plus psi of u is greater or equal than 0. Okay, so this can be seen in this way. So if I look at phi of x plus psi of u, I should just write, so this is f of x plus, so the definition is there. I should sum, you see those two, okay? So then I will do this way, f of x plus f star of minus a star of u, and then plus g of u plus, sorry, g star of u, and then g of ax, okay? Now I use just a Young inequality. This is greater or equal. The first one is just the scalar product between x and minus a star u. And the second is just the scalar product between u and a of x. But those two are the same quantities. This is 0. Okay, they are opposite. And so you prove this, okay? So what this inequality says is that, you know, the images of the primal objective and the dual objective are separated, okay? So the situation is, let me see if I, the situation is this. This is x. Let's assume that this is phi. And then you have here, this is the dual space y. And let's assume that this is minus psi, okay, this one. So you have that the function phi is always above the function minus psi, okay? This is the primal problem, which live in the space x. This is the primal variable. And this is the dual problem, which lives in the space y. And the values right, of the primal problem are always above the value of the dual, seen as a maximization problem, okay? So the max of minus psi. This quantity, so what, of course, they are separated, right? The two images, so that means that the inf of phi is greater or equal than the sup of minus psi. The sup of minus psi. Okay, I have this relation between the inf and sup, and the difference between those two is called the duality gap. Okay? So the duality gap is just the difference between the optimal values. Okay? So the theory of duality is about, you know, solving the dual problem instead of the primal somehow, okay? So it's about transforming your problem in another one, which hopefully is easier to solve, okay? That's and in order to do this, a minimal requirement is that this duality gap should be 0, okay? So we need to find condition for which this duality gap is 0 in order to connect the two problems and then to solve the dual instead of the primal. That makes sense, okay? Otherwise, it's useless. So there are conditions for this to hold, and normally they are called qualification conditions. Okay. So in order to introduce this qualification, so there are various qualification conditions. So in this context, I will give you so they can be introduced in this way. So if you look at the primal problem, okay, a primal objective, which is phi, I think, so you have the form of phi is f of x plus g of a of x, okay? And the function that makes this objective are possibly can take infinite values, okay, you have to be sure that the domain of this composite function is actually non-empty. So at least this function, so this function is not always plus infinity, okay? So then you ask that this function is, so a minimal requirement for the problem to make sense is that this function is proper. Okay, and proper means that the domain of phi, so the primal objective, is non-empty. So the domain is the set of points at which phi is finite, okay? You ask this, and because of the form of phi, this is equivalent to say that there exists a point x in x such that f of x is finite, but also g of x, a of x, is finite, okay? And this is the same as there exists an x in the domain of f such that a of x is in the domain of g, okay? I can write in this way, this condition. And now this is essentially, if I call this u, this is the same as, can be written in this way, 0 belongs to the domain of g minus a of the domain of f. So if this means that 0 can be written as the sum of an element here and an element here, okay? And if there is an x for such that a of x is in domain of g, this will be the element here, and of course this is also here, and so the difference is 0, okay, and vice versa, okay. So this is a minimal requirement. The qualification conditions ask a little bit more than this. So qualification conditions ask, for instance, that 0 is in the interior of this set. Okay? So I'm asking a little bit more. It's not only that 0 belongs, but it is in the interior. You can relax a little bit this. There are various notions of interiority. You can, you have a relative interior, strong relative interior. There are a number of weaker conditions that you can consider that now I tell you the theorem, ensure that the duality gap is 0, okay? So this is the qualification condition that I will consider. I will also tell you that, so I didn't mention this, when the duality gap is 0, so the optimal values of the primal and dual problem are the same, we say that strong duality holds, okay? Strong duality means that the duality gap is 0, so the optimal values are the same, okay? Normally, instead, the relation that, the primal problem is above the dual, somehow it is called just a weak duality. Strong duality means duality gap is 0, okay? So strong duality, so by definition, means that the inf of phi is equal to the sup of minus psi, or if you wish, minus inf of psi, okay? That's the situation. So we want to have, the point is that we want to have conditions that ensure this. Yes. Yes.
Sorry, you require the closure of the domain of G minus A of domain of F? Because you put the...
Say again, I didn't understand the question.
You require the closure of the domain of G minus...
Oh, sorry, no, you're right. No, I don't know why there is this line.
Oh, okay.
It was just because, okay, there was the underline, was to underline this, but then I decided to put this. Okay, it's not that, okay, so the qualification condition is this one, now is a box, okay. There is no closure. Thanks.
Can I make a comment?
Sorry?
Can I make a comment?
Yes.
So the comment is, so we saw duality for optimal transport.
Yes.
Actually, in the end, we didn't do the Lagrangian trick, but
yeah.
So just the comment is, this setting is good also for you know, doing the duality for optimal transport, and
Yes.
actually it works. The problem is there are two problems, I think. So one is that X is the space of measures, and
Yes.
so it's not an Hilbert space.
Yes.
And
But this works actually even in Banach and topological vector spaces.
yeah, but
you
then
you have a slightly different conditions.
but then I think that the problem is that the qualification condition does not hold for the duality in optimal transport.
So I will make this point now.
Okay.
So maybe it answers, because I think that in optimal transport you do this. So this is one. Okay, is the so the theorem is, and then I will. So the theorem is. So if qualification condition holds, if qualification condition holds, so that one, then you have that the dual problem admits solution. So strong duality holds. Okay, let's say. So strong duality. Duality holds. And actually the dual problem admits a solution, okay? So normally this is written in this way, in a compact form. So it is written in this way: inf of phi is equal to, say, for instance, minus the mean of psi, okay? So when I wrote this, I mean that, of course, the optimal values are the same, but here I put min to indicate that actually this is a minimum, okay? It has solutions, okay? So this condition does not only ensure strong duality, but actually that also the dual has solution. Okay, so coming back to the comment by Simone, since I said at the beginning that the dual of the dual problem is the primal problem, actually you can consider also this condition. 0 belongs to the interior of the domain of f star minus, and it's a plus, a star of domain of G star. Okay, so I can consider this analog condition for the dual problem, okay? But the dual of the dual is the primal, and so the optimal value, I'm playing with the same optimal values. So this condition also will ensure strong duality, okay? And will ensure strong duality and existence of the primal solutions. Okay, so depending on the situation, it might be that you can ensure this instead of that one. I think that in optimal transport, maybe you are able to do this. So I once verified. Of course, in optimal transport, so I'm talking about the situation which is, with compact space. So you have, in a more. So, and I will show you a situation in which actually in also in the problem that we will look at, which is this of regularized empirical risk minimization, actually is this one that is satisfied, okay? Okay. Another things that I need is that I need to talk about the KKT conditions a little bit, and then I'm ready for. So, okay, let's give this theorem. Let's call S the set of solution of the primal, so it's the argmin of phi. S star is the argmin of psi. Then I take 2 points, which is x bar in X and u bar, which is in Y. Okay, so the following are equivalent. So A, so x bar is in S, u bar is in S star, and the inf of phi is equal to minus, is equal to the sup of minus psi, the same. B, so phi of x bar plus psi of u bar, this is 0. Sorry. Okay. And C, okay, so now I need to remember. Yes. So it's minus a star of u bar belongs to the subdifferential of f at x bar and u bar belongs to the subdifferential of g at a x bar. See? So minus, yes. And of course, the dual of those are that x bar belongs to the subdifferential of f star at minus a star u bar, and ax bar belongs to the subdifferential of g star at u bar. Okay. So those two conditions are called KKT conditions. Okay. So you see now, so this says that x bar is a solution of the primal problem and y bar is a solution of the dual problem. Okay. And also strong duality holds. And those are equivalents. Okay. So this one, so the point is, so it's clear, for instance, that A and B are equivalent, okay, because this is just the optimal value, right? And this is also the optimal value, so the sum must be 0 in this case, right? So now the point here is that if you look at this sum, so as before, if you consider fx bar plus psi u bar, this is nothing that f of x plus f star minus a star of u bar, this is bar, and then say plus g star of u bar plus g of ax bar, right? This is just the sum of these two quantities, okay? Now what I do is that, okay, here I subtract the scalar product between x bar and minus a star of u bar, and here I subtract u bar and ax bar, okay? But actually, so this is minus and minus, but these again are opposite, so I did nothing, okay? It's 0. But now I know, because of the Young inequality, this is greater than 0. And this is also greater than 0. Okay? So the sum is 0 if and only if those two are 0 separately. Okay? But then once this is 0, this means that we characterize, this means this. Okay? Is the characterization of the subdifferential. Okay? And also, this is 0 if and only if, you know, when you have equality in the Young inequality, then you characterize the subdifferential, is this condition here, okay? So you see that this condition here is equivalent to this, and this is just the fact that the subdifferential of f is the inverse of the subdifferential of f star, okay? They are inverse to each other. I just swap these two, okay? So the point of these KKT conditions is that once you ensured somehow that strong duality holds, this provides you, the KKT condition provides a characterization of primarily dual solutions. Okay, that's it. So you ensure, normally you ensure strong duality, you know, with other, considerations, say. And then the KKT conditions, which are those, provide just, as long as you verify this, you have that, primal and dual solutions. Okay, I think this, I can then start. Okay, no, I need just to, let me see. Okay.
Sorry.
Yeah.
Yeah. For the last theorem.
Yes.
Yeah. We have equivalence between all the assertions.
Yes.
Okay.
I'm listening.
For all spaces X and Y, or
What means what X and
If-
Y are Hilbert spaces in this context, general, yes.
okay.
So the setting is that of this Fenchel-Rockefeller duality, right? So we are looking at this problem, right? Minimization of f of x plus g of ax. So we have two functions, f and g, that are defined on different spaces, possibly x and y. And then you have that those spaces are connected by a bounded linear operator that goes from x to y. That's the setting. And that's the, so in that setting, that conclusion holds.
Okay.
Okay. So, as I said, now, you know, duality is about, strong duality is about connecting the two problems, right? What I actually want is a little bit more, because I want to actually a way to, so the ultimate purpose is to forget about the primal. I will concentrate on the dual, but once I have a solution of the dual, I should have a way to obtain a solution of the primal, okay? So in order to do this, we need an additional assumption, which is this, that F is mu strongly convex. I mean, you can ask more or less, but mu strongly convex, okay? So in the primal problem, F strongly convex. So what you gain when you have this situation? So you gain two things. So the first thing is that the primal problem admits solutions, okay? P admits solution. Why? Because, so F, the objective is lower semi-continuous. So it is strongly, so sorry, it's not admits solution, it's more, has a unique solution, of course. So the uniqueness is because it is strongly convex, in the sense strict convex is enough, but you have also existence, because a strong convexity means that you have also coercivity, okay? So coercive plus lower semi-continuity means that there exist solutions, okay? So the first fact is that P has a unique solution. The second fact is that the domain of the F star is X, the entire space, okay? And also that F star is 1 over mu Lipschitz smooth. So that means that this function F star is differentiable and the gradient is Lipschitz continuous with constant 1 over mu, okay? So so now if I look at the KKT condition then, so there is the first one that we wrote, which is, it was that X bar belongs to the subdifferential of F star at minus A star of U bar, okay? That was the first, you know, of the KKT condition in the point C, I guess. So now this function is differentiable. So this subdifferential, it is actually a gradient, okay? So now this becomes X bar equal the gradient of F star, okay? And now you see, this is U bar and this is X bar are the solutions, okay? So this is actually is a way to get the primal solution once you get a dual, okay? So then you can, you have to imagine the situation in this way. Again, if I look at this situation, X now is here is phi, and then I have, this is y, and then I have, now let's assume that, okay, so let's assume this way. Okay, so this is the dual problem. This is the primal. On purpose, I set this not necessarily strongly convex. You may reach you have a plateau, kind of. So you put y bar here, and then you are x bar here, which is the solution, and this is linked between the map, which is gradient of f star, composed with minus a star. Okay, so that's the mapping that link the dual variable to the primal variable. Okay, and it's a single varied mapping now. Okay, so once you have then a solution of the dual, which is not necessarily unique, okay, then you can get the primal solution. Okay, applying this mapping. Okay, this map will also serve as another purpose because, you know, and I will show you now in a moment, normally you solve, of course, the dual problem approximately, right? You will apply an algorithm, right? So you will never get exactly U bar. You will be close to that, right? And so you also need that the mapping that connect the dual space to the primal space is kind of stable, okay? So because in the end, you want that to be close to the primal, okay? And this will serve also to this purpose, okay?
Again, may I add a comment?
Yes.
So this is, for example, the case of entropic optimal transport,
Yes.
but where F is strictly convex.
Yes.
So you get just that the gradient is continuous.
Yes.
And in fact, we have the representation of gamma as gradient of F of the dual.
Yes.
And in that case, is precisely a case where we don't have uniqueness of the dual, but
yes.
every, you know, moving with the constants, you get
yes.
always the same answer.
So, but in that case, it's strictly, so you have just continuity then, right?
Yeah.
Okay. So in this case, you will see you have a stronger inequality actually, because the assumptions are stronger. So what is, so what you do is this one. So the theorem is this. So you have that you define x bar, which is gradient of f star at minus a star of u bar. But then, okay, you say, okay, I have another u, and I define then the x in the same way, minus a star of u. Okay, I pick another u, okay, different from, possibly different from u bar, and then I define the corresponding one, okay, in the primal. So then the following holds is that mu over 2 x minus x bar square, this is less or equal than psi of u minus psi of u bar. And this is actually the minimum, okay? So here is, you know, you have a stability result somehow, because it tells you that if you minimize this objective, if you make this close to this, actually you will have also that this x will be close to x bar, okay? And you can control explicitly by means of an inequality. That also means that if you have a rate of convergence here, you can derive a rate of convergence here, okay? This is more nicer situation. Yes.
Sorry, is this just a consequence of the fact that when we are near to the minimum, we have a gradient which is almost zero, and then the mapping is through the gradient?
What is a consequence of? So this inequality.
Yeah, somehow this inequality.
No, this inequality is really because you have a strong convexity of F. Okay, if you ask for strict convexity, you won't have this inequality anymore. Okay, because this tells you is not only, you know, it's this is a strong somehow results. Okay, because it always this holds for any x. Okay, it's a global relation. It's not only local.
Okay.
So yeah.
Okay, so it's a somehow a global property of.
It's a global property. Yeah.
Okay.
Yeah.
Okay.
Yeah.
Okay. Thank you.
Okay. Welcome. So, and this inequality is the basis. You saw, I think, a number of algorithms, right, for minimizing convex problems. There is, all the algorithm that you saw. I don't know if you proximal gradient, FISTA, accelerated methods, whatever. There is, a dual counterparts of those algorithms. You can apply that. Is essentially means that you take those algorithms, you apply on the dual, and then you derive on the primal. Okay. Yes. Yeah. Welcome. No problem.
Just to understand if I'm
you're welcome.
attached.
No problem.
Because my understanding of the transform that you showed us.
Yeah.
I don't know if there's like something sacrilegious to say, but it's just that
mathematics nothing.
It's just something that, I mean, if it's something that you use when you want to see the information that a function is conveying in terms of its derivative.
So the transformation, which transformation? The differential conjugate.
Yeah, exactly. That
no, the differential conjugate. So you are physician?
Yeah.
Physicist, sorry. Physician says physicist, sorry.
Yeah.
It's the Legendre transform that you apply
exactly.
in the Hamiltonian.
Exactly.
It's that one.
Yeah, there I assume.
And so duality is about, it's a dual description of the function, because then you describe between with slopes, right?
Exactly. So in terms of the derivative, you are describing the function using as a parameter somehow
but you say derivatives because here there is no, we are not assuming differentiability.
Oh yeah, okay, I see.
Okay.
I see.
So, but it's a sort of.
Okay, let's say a sort of, yeah. So what you are saying is that this working in this space introduce you a mapping that exploits the gradient somehow, because they are the connection is between the gradient of the function you are exploiting and your primal variable. So if you can, okay, maybe I'm picturing this too.
I mean, of course, you are describing, the function by means of slopes,
exactly,
right? Of envelope of slopes.
Exactly.
Somehow this is
Yeah. So when you're close to the minimum,
but this is but duality works always in this way, right? Even in geometry,
okay,
is this.
Okay.
So
okay.
yeah,
I have to let it think a little bit more. Okay, thank you. Sorry for the interruption.
No worry. So, okay, so I won't prove this, but it's something that can be proved. Now, I want now to jump into the other problem. Otherwise, so let me just see if yes. So if you wish, I have something written, so I can even share this if you. There is this proof is also. Okay, so now I want to instead want to show you how this framework can be applied to the problem of empirical risk minimization, regularized empirical risk minimization. And you will see also how the kernel then, pops up somehow. I'm looking, I always forgot the eraser. Maybe is this one? No, but there was another one, indeed. Okay, maybe this. Now, okay. I always lost it's my characteristics. Okay. So now I think you have the right framework. We have the right framework to look at this. Okay. So the problem again, what we have is I remind you that we have the training set, right? X1, Y1, and then X and Yn. And this is our, say, in the space X times Y, X calligraphic and Y calligraphic input space, output space, okay? We have N of these points. Okay, so what we should look at, okay, we have also a loss function, which is from, say, R times Y to R plus. And this loss function is, L is convex in the first variable. And the problem is of the empirical risk is somehow to do this, right? Is the minimization over a certain function in certain space of 1 over n sum I1 to n L. Then there is yi f of xi, and then there is plus lambda, and then the norm in some space, right, of this function here. Let's assume it's our Hilbert space of functions. This is the problem of regularized empirical risk minimization. Is the framework. I think, I don't know if Ernesto called it also ridge regression, maybe. So the ridge is because here you use square, okay? So the point,
you have to invert f of xi.
Thanks. So the point here is that this problem in principle is an infinite dimensional problem, okay? And also we have to specify which space we are considering H, okay, here. Okay, so again. So I will then introduce now the so-called reproducing kernel Hilbert spaces, because this is the setting which is normally used, and but in a different way, so via feature maps, and you will see. So I will, for the moment, remove this, and I will define. So what we assume is that we have a map. So since the primal and I denoted the primal problem with phi, okay. So I will denote the so-called feature map, capital lambda. It's a map that goes from X to an Hilbert space H. This is not necessarily an Hilbert space of function. It's just an Hilbert space, abstract Hilbert space. Often it is L2, small L2. So from X to H, and I'm considering function of this form, say f of x equal to w, and then capital lambda of x, where w is a feature, say, okay? So it's just a way to parameterize function, okay? The parameter is this w that lies in a Hilbert space. So it's an infinite dimensional parameter. And I will describe this type of, I will consider this type of functions, okay? So that means that I will consider the space H, capital H, which is then from X to R of this form, okay? So that means that, exists W in H such that F is W and then dot. Okay, this function here, this function space. So this function can be endowed with essentially with a norm, which is actually then an Hilbert norm. This in general can be defined in this way. So is F is the infim of the norm of W with W which is in H and F which is W dot. Okay, so is the infim, so among the, so it might be that I can represent the same function with different parameters. I will comment now comment on this in a moment. Then in that case, you take the infimum of all this, okay? And then you can prove that actually this is an Hilbert space of function. Is actually a reproducing Hilbert space of function. So this H is a reproducing kernel Hilbert space, and the kernel is this one, x prime, scalar product between is just the scalar product between the feature map evaluated at x and x prime. Okay, this is the way the kernel then is defined. Okay, concerning here the uniqueness of the representation of the function, you have uniqueness. It's simple to see when you take the image. So if the image of this map is a total set, they say. So that means that you take the span of the image, you take the closure, and that must be H. Okay, so if gamma X, okay, the image of the feature map. So, sorry, if the span of the image of X, and then you take the closure, this is H, okay? Then you have uniqueness, okay? Then, you know, for each F, you know, there exists a unique W such that F is equal to W. Okay, this can be proved. And so in that case, the norm of F is equal exactly to the norm of the parameter, okay? Okay, so then if we consider this kind of parameterization, we can rephrase the empirical risk, the regularized empirical risk minimization problem in this way. So minimization now is over the parameter W, H of 1 over n, sum I1n, the loss, and now is W. So the order is correct. First, gamma xi, scalar prod, and then yi, and then plus 1 over 2, no, sorry, lambda. I will put 2, and then this is W square. And then, yes. So this is the problem we will look at, okay? Okay, so again, I want to stress that this is an infinite dimensional problem. In principle, you know, we don't know how to solve this because it's an infinite dimensional problem, okay? Okay, now I want to put this problem in the framework that we saw of the Fenchel-Rockefeller duality, okay? And we will compute the dual of this. You should notice already that, for instance, this is strongly convex. There is a term which is strongly convex, okay? And hidden here, there is an linear operator. Okay, so we need to find, you know, who is who. So the operator A is this one, H to Rn, and A of what is W is nothing that scalar product W capital gamma x1, and then W capital gamma xn. Okay, it's just you know, the list of this vector here. Now then we need also the f of W. Now the variable is W. Okay, f of W is just that. Okay, I will do this way. I will divide by lambda, so I will have lambda here. Of course, it's the same, but just to so then this fw will be 1 over alpha W square, right? And the G, so G, the function G is this one. So it's G of zeta will be 1 over, it's nice, 1 over n lambda, the sum I 1n. So I will define this way, L of okay, this way, minus zeta I and then yi. So I will define the G in this way, okay, where zeta is in Rn, and this is obtained in this way. Here I put a minus for reasons that are linked to the fact that in the end, I want to obtain, for instance, the representative theorem with the right sign. So I need to do this, but it's, you know, it's just, so once we have, so with these, you know, definitions, I can write down the problem, the primal problem, in this way. So our primal problem is this minimization over W of, so is G, okay, F of W plus G of minus A of W. Okay, so I put minus here. There is minus in here also, and so they cancel out. Okay, it's the same. But it's only because I need, so our operator is minus this, because I needed the dual to be without minus, and well, okay. So here is the form of the Fenchel Rockefeller duality. So the dual of this problem is then minimization. I will denote the dual variable in this context is common with alpha, okay? Alpha is in Rn, and it will be G star of alpha plus F star of now is A star of U, okay? There is no sign because the minus here is minus of the minus is A star, okay? So this is the form of the dual problem.
A star
okay?
alpha?
Yeah.
A star alpha?
A star alpha, thanks. So, and now we see we should look at this form, okay? So the first point is this. What is A star? A star goes from Rn to H and has this form. It's easy to compute. A star of alpha is actually the sum I1n of alpha I and then capital gamma of xi. Okay, it's just you know, is just the map that to some coefficients associate this vector. It's a linear combination of the feature map evaluated at the training points, okay? The second point is, okay, F star. F star is easy because F star is nothing that it was, is this function, right? This is, the dual of this is the same function. Okay, so it's 1 over half, is 1 over 2, and then now is, sorry, this is, I should put now, say V, okay? It's the dual variable, let's say square. Here is in the Hilbert space. F is defined on H, and also F star, of course, will be defined on H, okay? So this is the function, the dual. And for instance, then here, then we can understand this term, okay? So this term, F star of alpha star, then alpha, is nothing but 1 alpha, and then the square of the sum, the square norm of the sum of alpha I gamma xi square, okay? This is the term. And now you see this is a square, so this can be, of course, developed. And so this is 1 over 2, the sum over I and j of alpha I alpha j, and then the scalar product between xi and then gamma xj. But now that's the trick and the important point. This is the kernel by definition, okay? So this, in the end, can be, so if I define, this is actually what is normally called the Gram matrix. So it's the kernel evaluated at the training points. So I will define, say, I will do not say, oh, so with kappa, say more, is the matrix. So is Rn times n, and the entries of this matrix Ij are nothing that k xi xj. Okay, so then in this, so with this position, say this F star alpha, this term can be written as 1 over alpha and then kappa alpha alpha, or if you wish, is 1 over alpha, with alpha transpose, and then alpha, okay? It's just a quadratic term, okay? So you see that now here we have just a quadratic term that involves the Gram matrix. And here we will discover now this term also. Okay, so let's see. So G is of this form. Okay, this can be written as sum I1n of GI ZI, where each one of this GI, say of T, this is 1 over n lambda L of minus t yi. Okay, so this this function here is separable. The fact that you have gi, zi, so it acts component-wise, okay? And each one of these gi has this form, okay? So then you should know that if I compute the dual of that one, G star, it is also separable. So this G star of now alpha, this is sum I 1n gi of alpha, gi star of alpha I. Okay, it is also separable. And so it's, I need just to compute this gi star, okay, which is a function of one real variable. Okay, I will compute it here. So this is gi of, say, S star. This will be the sup over T of ST minus gi, which is here. So then will be 1 over n lambda. And then there is L of minus T yi. And so I will bring this constant out. So this will be 1 over n lambda. And then here I will write the sup over T. And here I will have minus Sn lambda times minus T, and then minus L of minus T yi. Okay, I just bring this, so I need here to multiply by Sn, and then I put 2 minus, because here I have the minus. So then you may recognize that this is just 1 over n lambda, and here is the Fenchel conjugate of L with respect to the first variable computed at this point. So it's minus Sn lambda, comma y. Okay? So now I have all the pieces to see what is the dual, okay? So the dual problem is this. Minimization over alpha in Rn. So there is, so it was 1 over alpha, then I will write in this way. So kappa alpha alpha is the quadratic term, and there is plus 1 over, so is, I wrote there, is 1 over n lambda. Then there is the sum I 1 n of L star minus alpha I n lambda and then yi. Let's see if it is correct. I think so. Yes. Okay. So this L star is just the Fenchel conjugate of the loss in the first variable, okay? Is the conjugate, is the transform of a function of a one real variable, okay? So it's something that normally you can compute. And actually in all the losses that you may consider, so the least square loss, the Inge loss, logistic loss, Uber loss, whatever loss you like, you can compute this explicitly, okay? So now I want to stress this fact. So normally so there are two problems in the primal problem. The first one is that it is infinite dimensional. The second one, which is that it is written in terms of the feature map. The feature map is something that you don't know. Okay, if you take the Gaussian kernel, the feature map is complicated. Okay, so so then that means that you normally don't want to deal with feature maps. You go to the dual, and then something kind of miracle happens, is that the feature map does not appear anymore, and you have the kernel. And the kernel is something that you can access to, okay? So here you need to compute, here there is the kernel, it's finite dimensional, and everything here is computable. And the relation between the primal, so the point is, the important thing is, okay, let's look at the KKT. If you remember, the first one was X, okay, in this new notation is W bar equal the gradient of F star, now computed at A star, U alpha bar, okay? But the gradient here is the identity because f star was 1/2 the square norm, right? So here is the identity. And so the first of the KKT conditions is nothing that sum 1n alpha I bar and then gamma xi. So this is what is normally called the representer theorem. Okay? So maybe here there are no people from the machine learning community that grow into, but there have been a lot of papers on deriving this representer theorem, okay? But you can derive it as just the first KKT condition of the problems. That's it. And this holds for any loss function. Okay, instead you can find paper that okay, let's assume that the loss function is smooth, then non smooth. Okay, it's just, and the fact that it is of this form, it only depends on the fact that the regularizer is the square. If you change the regularizer, you don't have a linear, you will have that this is nonlinear. Indeed, you may try to do this, for instance, in Banach spaces, so regularizing with the norm. Then there is a problem because then the kind of representer theorem is not linear anymore because there will be this part, okay? Then it simplifies just because you regularize with the square. So for this ridge regression setting. And the other miracle of course, once you have this, of course, you don't care about the parameter itself. You care about the function that is represented by this parameter, right? And so what you have is that if you consider the associated function, which is, say, fw bar, this is obtained by w bar and then gamma x, capital gamma x. But then if you use now this representation, this is the same, you can recognize this is nothing that I1n alpha I bar, and then the kernel again at xix, okay? So you see that if you want to evaluate, if you want to make a prediction, you need just to know the dual variable, okay? So everything is expressed. So the quantity of interest in this, in this method are always expressed in terms of the kernel. And that's the reason why they call it this kernel trick. And these are the basis, basic idea of kernel methods, because everything is expressed in terms of kernels. You don't need other, and it's a way to, this is in principle is not straightforward, right? Because you are dealing with an infinite dimensional array. It's a non-parametric estimation problem. It's infinite dimensional, but with this kind of kernel tricks, which means going to the dual, everything is fine and nice. Okay, and okay, so other comments? I don't know. So the time I have still, how much time I have? Because depending on how.
Yeah, more or less 10 minutes.
Okay, okay.
15 minutes, I don't know.
Okay,
yes.
So okay, I can tell you this then. So if there are any questions, ask. Don't be shy. So for instance, okay, just because we are once
in practice.
Yeah. Sorry.
In practice, how we compute the kernel?
Sorry.
In practice, how
you have a form of kernel, right?
We have to choose the kernel.
So the kernel, you have to have the kernel. Normally, you have if you use Gaussian kernel, there are a number of kernels that you may use.
So we choose the kernel a priori.
Yes.
Okay.
Yes.
And
yeah.
Just about the first equation of the problem.
Yes.
At the beginning, you said you proposed the minimization problem on F, which belongs to H.
Yes.
Calligraphic H.
Yes.
And then you propose a problem on
the W.
On W with classical H.
Yes.
And,
is equivalent.
But between these two statements,
yes,
you did not define the inner product on H calligraphic.
on H.
But
Yeah,
but
yeah.
you gave the norm.
Yeah, it can be defined. Okay.
Okay.
Actually, you don't
Because
that norm there can be proved to be a Hilbert space, Hilbert norm. Okay, so it is defined by means of a scalar product, of course. The way to define this scalar product is a little bit delicate.
Because the definition of the norm is an infimum. So my question was, how can we pass from the inner product to the infimum?
Yeah, it is possible.
Okay.
Yeah, I can. So I can give you reference if you wish.
Okay, and what's the difference between the classical Riesz theorem and the moment when you define f of x, w as the unique parameter such that we can define f of x? Is it a generalization of Riesz theorem? Or
no, it's about so you are in a Hilbert space. You parameterize your function by means of this w. Okay, you write this w scalar product with the capital gamma, this feature map evaluated at x. Okay, so once w is fixed, you have a certain functions that, of course, it will depend on the feature map and so on the underlying kernel. Okay, the point is just it was a comment on the fact that you may represent possibly the same function by different parameters. Okay. By the way, even if you don't, for instance, in this formulation, in that formulation there, right? Since this is equivalent also in the case in which you don't assume uniqueness of the representation, because if I put that so the norm of the function f is an inf.
Okay.
So you have a min of an inf in the end is that same problem. Okay. The uniqueness is often satisfied, and it really it depends on the feature map on this. So often you have that you span or you discuss. So yeah, it's a condition that ensure just that you have uniqueness in this representation. Okay. Okay, it's not related to the Riesz theorem. Okay. Yeah. Because it's about, okay, maybe I can tell you more later if you wish. It's about so you should consider an operator that associate to each w the function, okay, and this operator, you need to ask that this operator has zero kernel, so the kernel is zero, because you want injectivity of this map. And so the normal so once you if you ask for this the kernel to be zero, is the same as so you can see that it's about asking that the image is a total set, they call it. So it's so if you take the span of the image and the closure must be H. It's I can tell you more if you wish later. So I want just to tell you in these few minutes that remains just the form of this dual. So of course you have this. So using the fact that you have a strongly convex, so the concerning the algorithms and dual algorithms. So what you have is that so if you consider the function f, which is so f bar, which is the regression function, say, which is this. So this is the solution, and then you have another one which maybe comes is an approximation that comes from an algorithm, okay, with another parameter, possibly close to w, right? So if you then look at f bar or say f of x minus f bar of x, okay, you look at this quantity, right? So this is the regression function. This is the function, the target function, at possibly a new point. and this is your approximation that comes from the fact that you are solving the problem inexactly, right? Because it comes from an algorithm that solved the dual. So this, you know, this is W might be sum of alpha I of xi. And this alpha is just an approximation of the alpha bar, okay, the right one. So this is the same as W minus W bar, and then gamma x. So you use this representation of the functions. So you apply Cauchy-Schwarz here, and then you get W minus W bar. And then here there is the norm of capital gamma x, okay? And now you remember that since the function f is strongly convex, the following inequality holds. So we have that 1 over 2 W minus W bar squared. This is less or equal than psi of alpha minus the minimum of psi. Okay, you have this relation. And therefore, here you have that this is less or equal than square root of 2 times, and then there is psi alpha minus the minimum of psi. And this is nothing that the square root of kxx. Okay, if you take the square, this is kxx, and then so this is times. Okay, so you have this bound, and as long as, so this tells you that if this alpha is close to the minimum, actually you can control this quantity, which is, this is the quantity that you use for the prediction, okay? You are close to this. And often this is uniformly bounded, the kernel, yes.
Sorry, I didn't quite get the way in which you do the last inequality.
The last?
Yeah, the last one, like which was the connection with, because in the
this one?
Yeah, exactly.
Okay, I just remind this result.
Yeah.
Since so in the framework, right, of this Fenscher-Rockefeller duality, once the function f is strongly convex, we get this inequality.
Okay.
Where W and W bar are connected with alpha and alpha bar respectively.
Okay.
Okay, by means of the way you go, right? Now it's a linear operation, say.
But is it something that we have already seen, or is
something, sorry?
That we have already seen during the lesson, or no? Or is it something new?
So I show this inequality for general, you know, in the general dual, you know, this, once you take f, which is mu strongly convex, you have this inequality with here, which is mu. Okay, now mu is 1.
Okay.
And so I get this one, okay, in this specific case. And here, okay, here, I mean, the relation is that this W bar is nothing, the relation is the representer theorem, okay? Is alpha I, gamma xi, and W is obtained the same way. So with a general alpha I, okay, which is not necessarily the optimal. And so you can think of this coming from an, you know, an approximation, okay? So then you have this relation, and then you have this situation. Often this can be bounded, okay? This is uniformly bounded. So you have square 2 psi of alpha minus the mean of psi, and here you have times the sup of this quantity, which is finite often. Okay, so in this situation, you have a uniform bound. So actually you have, you know, you can bound actually the L f minus f bar infinity. Okay, this is less or equal than 2 and the same quantity, and this is a constant, say, C. Okay, so you have a uniform bound on the functions. Okay, this is the, so, you know, this is the quantity that you really care of. Okay, because you are making predictions. Okay, so the last comment is that this problem here you see is there is a quadratic term. If you take, for instance, the least square loss, this is also smooth. So the problem will be smooth without any constraints. If you take the hinge loss, this will gives you a linear term plus a box constraint. Okay, so this will be then a smooth problem constrained with a box constraint, and then you can use, for instance, projective gradient methods to minimize the function, okay, the objective functions. And also it is interesting that you really just need to minimize the objective function, not to really, the rate of convergence that you possibly need is on the function values only, okay, in the dual. This will give you anyhow rate of convergence in the primal. There are other relations beyond these ones. Beyond this one, you may connect also, because you get this with hypothesis on F. If you make hypothesis on G, you can connect the dual objective with the primal directly objective, okay? Not necessarily this. And this is also important because often, you want to assess the quality by evaluating the risk. Okay, so it's important also to have a control on the objective function, on the primal objective functions, objective function. Okay, so yeah, I can finish maybe here if you.
Okay, so thank you, Saverio.
Okay.
And do you have questions, Saverio? No, also Silvia said that if they had comments or questions,
you can write
from from Silvia's lecture, they can ask you. So
okay,
you can ask also if you have comments.
Okay, thanks.
Yes.
Yes. No, you're not to have. Sorry, I mean, it's normally is appreciated that someone.
I'm still not getting this.
Okay, great.
This inequality about
like this one.
Yeah, exactly. So is there a scalar an inner product somewhere, or is it just like
there is not lambda?
Okay, so
you can cancel lambda. Lambda is not in the formula.
Oh, I see. I see.
The lambda at the right. You see the right. You didn't cancel lambda.
So what is bothering is maybe the way it is written. So it is this one. So okay, I don't know why. Okay, this is just okay. Sorry. This is okay. Sorry, my fault. Yeah. So I think that one comment is that really these are the so-called kernel methods. They apply also in various in other situations. Okay, even in kernel mean embeddings, there are other situations in which kernel methods can cover. And I mean, the theory underlying is always the Fencher-Rockefeller duality. Okay, you can deal with many situations. Okay, and this is just an instance.
Okay, so if there is no other questions, so let's thank Professor Salzo again.
Thanks.